So, hello everyone, welcome to the European Non-Associative Algebra seminar. I have a pleasure to introduce the speaker of today, Fernando Montaner from the University of Zaragoza, Spain. The title of his talk is Pairs of Quotients of Jordan Pair.
Okay, shall I begin? Okay, so thank you very much for inviting me to the seminar, and I'm going to speak about that, about the systems of quotients. Systems means Jordan systems of quotients of Jordan systems. Okay. Okay, I'm going to project my slides. It's here. Okay, so you can hear the slides. Okay, so I'm going to speak about this systems of quotients of Jordan systems, and well, okay, and so first of all, I'm going to recall some basic facts, some basic definitions of Jordan systems. So first of all, the most basic definition almost is Jordan algebra, but my Jordan algebras will be quadratic Jordan algebras. So in fact, these are it's the less basic. Sorry?
Can you make it full screen, please? Can you
I
make
made.
slide full screen, please?
Sorry, I cannot hear you. Can you speak a bit louder?
I mean, can you make a full screen? Can you make your slide full screen?
And sorry, I make
a full screen. Full
screen. Okay. Well, I don't know. I think I thought it was full screen. Just a moment. Okay. Yeah. Let me see. Okay. Just a second. Okay. No. Just a second, because I don't remember. Okay. But this is smaller. I think this is the biggest I can get.
Yeah, it is full screen. Yeah.
See, that's full screen. So I think this is the biggest I can get. Okay.
It should be in menu there. It should be something called presentation. Or...
Yeah, well, I'm going to look at that. Okay. But yeah, okay.
There.
I think here. Maybe this one?
Yeah.
Basically, they say this is what the most I can get, I think. Okay.
Yeah,
okay.
that's perfect.
Okay, so I'll continue. So I was going to speak about, so for my first definition is the first definition I'm going to recall is that of a Jordan algebra, and not linear Jordan algebras, but quadratic Jordan algebras is just a slide, well, not just a slide, but it's a generalization of the original notion of linear Jordan algebra, but which well, anyway. So this is the definition. So instead of having the usual bilinear product, you have a U product, which is something that you here it is in in terms of the product. This is as it is expressed here, and apart from Jordan algebras, there are some other Jordan structures, and so I'll pay attention to Jordan pairs. Okay, my Jordan pairs will also be quadratic in the sense that it makes the results independent from the ring of scalars. So it means that they can work in any ring of scalars, no matter whether it has a 1/2 or whatever. Okay, so this may be anything. Okay, so that's what we have. So the basic examples of Jordan pairs come from, well, in fact, the very definition of a Jordan algebra comes from associative algebras, and because you can get a Jordan algebra from an associative algebra by symmetrizing the product. So taking instead of x times y, the associative product, the product x times y plus y times x. And 1/2 of it, if you have 1/2, this is the original definition that was due to Jordan, and that's why it's called Jordan algebras, and it comes from an attempt to find a formalism for Jordan mechanics. Okay, so in Jordan pairs is a generalization of a Jordan algebra, which in fact is related to something that you can, well, that you can do with a Jordan algebra, which is well, instead of having just one linear thing, just one space or whatever, you have a couple of spaces, and so you can imagine them as, for instance, one example of Jordan algebra are the two corners of a matrix algebra. So if you take a P times Q matrix algebra, I mean, what is depicted here? So we have this is an example of a Jordan pair. I mean, this is an example of an associative pair. Okay, so you have two linear spaces acting on one another. So this is and this makes you you can get a Jordan algebra out of that, and that making a product symmetric in the way that it's depicted here. But these are very basic definitions. And also, if you have an involution, which leads to the original definition of Jordan algebra, because the original definition of Jordan algebra was aimed to capture the behavior of symmetric matrices or symmetric operators, which was their physical origin. So so that's why the product was symmetrized, and this symmetry, well, this symmetry of the product is well, what that was aimed to preserve was the involution, because you were speaking about the operators on Hilbert spaces, so they had this Hermitian structure, and so an involution of the ring of mappings of the spacing itself. Well, in generalizing that, what you have is an associative algebra with an involution, and inside that you have the set of symmetric elements that was the original example, and something that generalized the set of symmetric elements, which is this H naught of A, which is the set of this is a set of symmetric elements, but more general, more restricted than the original set of all symmetric elements. So this is what is called an ample subspace. Okay, this generalizes what you came across when working with Jordan algebras. And another example of Jordan algebra is you take two Jordan pair, you take two Jordan algebras, and then a Jordan algebra acts on itself as a Jordan pair. So you have the pair of Jordan algebras that makes a Jordan pair. And you also have another example, which is alternative pairs, and that's also something that you can rephrase in terms of a Jordan, an associative pair with an involution, and also by Kelly pairs, which are the so-called exceptional pairs, which are, well, these are never inside. I mean, they cannot put inside a pair of an associative pair. Okay, which is something similar to what happens to Jordan algebras. So you have exceptional Jordan algebras are the ones that cannot be embedded in an associative algebra with the symmetrized product. I mean, these are the basic examples of the notion of Jordan pair. Well, so what we're going to deal with is the idea of the ring of quotients, that of course is inspired by, well, this is inspired by the construction originally and from the very basic construction of the field of fractions of the ring of integers. Okay, and this leads to the localization theorem, which in fact is an important tool in commutative algebra, in algebraic geometry, and it led to generalizations to associative algebra and associative algebras and to Jordan algebras, which is what we are going to deal with. Jordan algebras and Jordan pairs, which are generalizations of Jordan algebras. Okay, so what is a ring of quotients? So you start from the associative theory. If you start from a ring, and you consider a filter of left ideals, then you can define a ring with the denominator filter as a set of another ring, a ring that contains your given ring, such that for any element of this other ring, the set of denominators is an ideal. Well, this is a left ideal. The set of denominators is described here is a left ideal that you ask is to belong to the filter that you are considering, and that it satisfies that it doesn't vanish the element Q. So this means that your element Q is visible from the ring R. Okay, so you can take your Q back to the original ring R, and by multiplying by the denominators. So the denominators, the denominators are essentially the same as your commutative construction of rings of fractions. Okay, but here you consider all the elements that can be multiplied by your element and take your element back to the original ring. Okay, so this is for this to work, to be able to construct a ring out of this idea, what you need is that the set of the possible denominators, the set of left ideals F, where you take your denominators, will be a filter. Well, in fact, this should be what is called a Gabriel filter. Okay, and using that, using the properties of a Gabriel filter, which basically are the properties of a filter, which makes this a topological, give the ring a topological structure, because taking this as the set of neighborhoods of the element zero, or the zero element, and this extra property, which makes this a Gabriel filter, apart from being a linear topological filter, allows you to construct not only a direct limit of the partially defined mappings from this filter, from the ideals, from this. If you multiply an element of this left ideal by an element Q of the ring, the over ring, of the ring of quotients, what is going to be the ring of quotients, what you get is an element from R. So the ring of quotients defines for the set of its left ideal of the denominators, it defines a mapping, a linear mapping, which is a partial multiplication of the elements of R by the element Q. Partial because you can only do that for elements that take this back into R. So for denominators, okay, so that's the idea. Well, that's basic localization theory for associative algebras, and we want to generalize that to Jordan algebras. So the original problem is the situation where it is the original associative generalization of these ideas further than commutative rings comes from Goldie theory. Well, in fact, it comes from the problem of constructing what are called quotients, rings of quotients, which is mentioned here, and this works when your filter of ideals is a set of, if it is a filter, the set of essential ideals of your ring. Okay, this is your filter of ideals. For this to work, by the way, what you need is for this to provide a ring of quotients, what you need is this should be the set of denominators of the elements. So there shouldn't be any element that kills that, such that multiplied by a large ideal gives you zero. This means that the ring must be non-singular. Okay, this is also technical condition. Okay, so this is a very classical situation, and what we do is to generalize this to Jordan. One idea of one important fact of this particular example, all these theorems, is that what you can get under some ascending conditions, Noetherian type conditions, is the most classical, I would say, the most classical kind of rings, which is Artinian rings. I mean, the non-commutative, the most classical non-commutative rings, which are Artinian rings. And so what this is something similar. I mean, it extends to non-associative, to associative rings, not necessarily commutative. The idea that from a domain you get a field, which is the kind of the best type of rings that you can get, or at least in terms of its representation theory, in terms of the of its category of modules. Okay, but so the corresponding fact would be Artinian rings. Artinian rings with non-nilpotent ideals. Okay, so semi-simple like the Artinian rings. Okay, so this is the definition of algebra of quotients, and so we want to extend that definition to Jordan algebras. And the idea is basically to take the same notions that I have just exposed for algebras, which is taking a ring of denominator, a set of denominators that will be an inner ideal. I mean, what corresponds to a left or a one-sided ideal in associative theory is are inner ideals in Jordan theory. Okay, so left ideals correspond to inner ideals, so our denominators should be inner ideals, and they should form some kind of well, of course, this is not set here. This should form some kind of well, as in the case of associative algebra, some kind of a linear, some kind of filter so that you can get a linearly topological ring for your Jordan ring. And also this condition, second condition that appears here is that your element in the other ring of your ring, the ring Q of your ring J should be, so to say, visible from your ring J, which means that the denominators shouldn't be annihilated by the element Q, which is in the over ring. So if you the denominators of Q. So this is the denominators are defined in this way, and this turns out to be an inner ideal, and this can be generalized, as we will see, to other Jordan types of Jordan systems. Okay. Well, so this is an inner ideal, and this is what we consider. And of course, we can say, okay, our inner ideal, we can restrict our inner ideal to some particular types of inner ideals. So, for instance, if you take as inner ideals the ones we do not meet the set of invertible elements in the over algebra Q, you're led to consider the so-called classical algebras of quotients, the ones that make invertible some elements that are regular in your original ideal, which is the idea of the construction of the field of fractions of a commutative ring, and also of the construction of the quotient in the Goldie theory. Another kind of rings is another kind of possible denominators are the inner ideals, which contain an ideal from the two-sided. An ideal, not just inner, just an ideal of the original algebra, and this leads to what that named martingale like algebras of quotients. Characteristic. I mean, if you have the 1/2 and 1/3 in your ring of scalars. Well, as a matter of fact, this is not really necessary. But anyway, I mean, that can be also generalized. But that's the original definition given by the authors of this definition, which were Esther Garcia and well, if you are considering essential linear ideals, as in the case of rings, you should ask for your ring to be what we call strongly non-singular, which is not just non-singular, but it means that no non-zero element has for non-zero element x of the Jordan algebra, the U operator of U sub x vanishes on the inner ideal of this essential linear ideal. Okay, so this is kind of U of x is non-zero on essential linear ideals, not just on the whole ring, original ring. So that's why this is called non-singularity, and this is a strong form of non-singularity, taking into account the definition of non-singularity for Jordan algebras. And also you have a notion of dense inner ideal, which generalizes a notion which is used in associative theory, and which embraces all the other previous definitions that, I mean, the previous cases that I have just mentioned. Okay, so this embraces all these, the case of and the classical algebras, of course. I mean, you can construct an algebra of fractions of, sorry, a localization for your Jordan algebra using this set of ideals. Well, and the definition of a dense inner ideal essentially means, well, if you recall what is a dense ideal in associative theory, a dense ideal is an ideal for which the annihilator, the elements that the elements, okay, so well, well, in fact, this is the definition that we adopt here is the one which appears in the slide, and what it does is, I mean, you have something with this same notation, K 2 points A in associative theory, but since associative theory is associative, of course, then K 2 points A, B, as I mean, if you do that procedure several times, since you can multiply the elements, you get one ideal of this type. This is not the case for Jordan algebra, so you have to define density, not multiplying, but iterating this construction. So this is the definition is the one which appears here. Okay. Well, using these ideas, I mean, in fact, not using these ideas. A particular case of these ideas is well, in commutative theory, what you want is to, I mean, in the most classical commutative case, what you want is to get a field from a ring of from a ring with non-zero divisors, and in the case of associative algebras, what you want is to get an Artinian, a semi-simple Artinian algebra from a set from a ring with the adequate conditions, and this can be generalized. I mean, this gives you what I call the Goldie's theorems, and so if under some conditions, some ascending chain conditions on some ideals, what you get as ring of quotients that is making invertible some elements which are not invertible in the original algebra. So on over algebra, which is for which the its regular elements are invertible, what you get is an Artinian, a simple or semi-simple Artinian algebra according to what your original algebra was, solely non-degenerate or just non-degenerate. Okay, so this is what is the generalization of Goldie's theorem to Jordan algebras. And that was originally proved by Zelmanov in the case of linear Jordan algebras, and generalized by Fernández López, Garcia Ruz, and myself to quadratic Jordan algebras. Not only generalized, I mean, we did not only generalize the original what the original theorem proved by Zelmanov, but also, well, extended that, of course, because we worked with quadratic Jordan algebras, and Zelmanov worked with linear Jordan algebras as usual at the moment. And also, in fact, its proof contained it contained a gap that we filled, but I will comment not on the gap, but on the tools to fill that gap later on. Okay. So what we have is this theorem, which generalized Goldie's theorem for first and second. I mean, the Goldie's theorem for prime Jordan, prime associative rings, and for semi-prime associative rings to Jordan algebras. Okay, and what it says is, okay, with the corresponding Goldie conditions as ascending chain conditions of annihilators and things like that. These are conditions that are satisfied by Noetherian rings. What you get is either a simple Jordan algebra or a semi-simple Jordan algebra, depending on whether your original ring was prime, strongly prime, or just non-degenerate. Okay, so this is the model of what we want to generalize to Jordan from the associative theory, but there is something which is peculiar to this situation. I mean, to the Goldie theory for Jordan algebras, which is the following. Of course, we want if we want to generalize the associative theory, we look at, I mean, it's just looking at what we want to get is, as for commutative, in the commutative associative theory, what you're going to get is a field. I mean, this is the most classical localization. In Jordan algebras, in associative algebras, would like to get either a simple Artinian simple algebra or Artinian semi-simple algebra. And for Jordan algebras, what is the analog of that? Well, there is a notion of Artinian, which is just copying the notion of Artinian of the Jordan theory, of the associative theory. So ascending chain condition and descending chain condition for inner ideals. But there is another more natural notion of, so to say, being good for a Jordan ring, which is having capacity. So having finite capacity, which is something that you can relate to the idempotence of the ring. And so the condition, a natural condition to ask for a ring of quotients would be, instead of being Artinian, would be having finite capacity, which means that you have a set of orthogonal idempotence. Well, anyway, you can coordinatize using idempotence through algebra. It's like the matrix units somehow. And so this gives you another type of condition for the good algebra you want to get as a result of your localization as a ring of quotients, which is instead of, sorry, did you say anything? Well, I'm doing what? No. Okay. Well, right. Okay, so here in Jordan theory, you have a different condition that makes sure that you have a ring of quotients of finite capacity, not just not Artinian, but just finite capacity. And the condition corresponds to something that is important in the case of associative algebras, which is that an essential left ideal in associative algebras, left or right ideal, so one-sided ideal, one-sided ideal is essential if and only if it has a regular element. Okay. Now, this condition can be translated, maybe transferred to Jordan algebras and say, okay, an inner ideal is essential in the sense that it meets any non-zero inner ideal of the algebra, if and only if it has a regular element. So an element which we name injective, which is an element for which the U operator is an injective mapping. I mean, this is, of course, has a consequence that its annihilator is non-zero, but this is the usual way of defining a regular element in Jordan theory. So making these elements invertible gave you, I mean, having the, asking for the algebra that the property of that an inner ideal would be essential if and only if it has an injective element, which is the generalization of and was one-sided ideal of an associative algebra will be essential if and only if it has a regular element. Well, this condition does not imply, I mean, this is not equivalent to being Goldie in the sense that you have an Artinian ring of quotients, but what you get is something which is close to that, which means that your ring of quotients is not Artinian but has a finite capacity. Okay. Now we know we call that in a paper. I will mention that later. In a paper by Maribel Tocon and myself, we named that Lessier-Croisot Jordan ring. Okay, I mean instead of a Goldie Jordan, these are the other two authors that worked on that problem in almost at the same time as Goldie. Okay, now so how to prove these results? Well, here a general principle is distinguishing the PI algebras satisfying a polynomial identity versus the non-PI algebras. This is a general fact for Jordan theory because I mean this is what gives you the structure theory of Jordan algebras, and the identities. I mean the polynomials that may or not vanish are the so-called theta ethers and so on. But this is part of the Jordan theory that I'm not going to review here. And so if you have an algebra which is not PI, then this is a special Jordan algebra. And if it is PI, this is an exceptional. Well, this is. I mean, you can easily, well, somewhat easily describe them. Okay. So in this sense, being PI is a very strong finiteness condition for Jordan algebras, and not being PI is kind of a generic Jordan algebra, and the generic Jordan algebra is the Jordan algebra of symmetric elements of an associative algebra, or more generally, an ample subspace of symmetric elements of an associative algebra. So this is what you get. And so what is the strategy? Well, the strategy is, well, if you have a PI algebra, then this is somehow a small algebra. You can work with that, and in fact you have idempotence there, and you can use the classical theory which goes through the use of idempotence. And if you have an algebra which is non-PI, then this is kind of generic, and then what you do is relating your algebra to the associative. I mean, this is contained in an associative algebra in this way, so you can relate your algebra to the associative algebra and transfer your problems from the original Jordan algebra J to the smallest possible associative algebra that contains G and J, the original Jordan algebra. And this is called the associative envelope of J. So the idea is, okay, you have a problem on J, and either this is a PA algebra, and then this is a problem on an algebra that can be described in a quite precise way, or this is an special algebra, and then you can transfer your problem to an associative setting through its associative envelope. And the way of doing that is, as it's shown in this slide, is okay. If you have a one-sided ideal, you can generate a one-sided. You have an inner ideal of J. You can generate one-sided ideal in the associative envelope, and if you have a one-sided ideal in the associative envelope, you can get an inner ideal of the Jordan algebra, just taking the intersection of the ideal with the Jordan algebra. Now, what is the obstruction? The obstruction for this going up and down of information work? Well, the abstraction it can be shown to be the existence of what are called PI elements. So elements such that the local algebra defined by them is a PI. The local algebra, we'll mention that later on, but basically this means, in a sense, what it means is that what you have is in the associative algebra, because for associative algebra, this is essentially having a generalized polynomial identity. So in a sense, the abstraction to the flow of information between an algebra and a special algebra and a non-PI special algebra and its associative envelopes is the existence of PI elements. So it's the existence of generalized polynomial identities in the envelope. Okay, so this is a case that should be considered independently, and it has been considered. So this led to the notion of PI element and the study of PI elements and so on. And this filled the gap in the original proof of Zelmanov of Goldie's theorem. So what we have is the following now. So this I have already defined what is a Lessier-Croisot Jordan algebra, and this is what I have already mentioned. And the set of Lessier-Croisot elements of a Jordan algebra form an ideal of the Jordan algebra. So and this ideal is quite interesting because of the reasons that you will mention in next. To any element of a Jordan algebra, and this is what I'm going to mention now is something which is basic in Jordan theory from its introduction by McCrimmon, which is the notion of local algebra at an element. The local algebra at an element comes from the, so to say, the homotope algebra modulo some ideal which is naturally which appears naturally there. So the homotope algebra is the algebra which has a U operator, the composition of U and of the element that you are operating in of U sub A. Okay, so in associative terms is inserting an A into each in between any two elements that you are multiplying. Now this creates an ideal, a trivial ideal, which is the set of elements that vanish when multiplied by A, and this gives you which is denoted the kernel of A, and the quotient of the homotope by this is an algebra of the an ideal of the homotope, and the kernel of the homotope by this ideal is what is called the local algebra of this element. And so the thing is the following. I mean the set of Lessier-Croisot elements the set of Lessier-Croisot elements is defined as the set of elements for whose the local algebra is an LC algebra. It's a Lessier-Croisot in the sense that it has the conditions that it has a quotient ring a ring of quotients, which has finite capacity. Now, if you have a strongly prime algebra with non-zero pi elements, then the Le ideal of J is exactly the set of pi elements. Okay, so this is this assertion here. This was proved by Tocon and myself, and the next point, which is important, is this local Goldie theorem for Jordan algebra. I will come back to this again. Which says that was proved by Paniello and myself. It says that the intersection of the Jordan algebra with the circle of a maximal algebra quotient, the maximal algebra quotient is the algebra of quotients defined by using the dense inner ideals as denominators. The dense inner ideals that I mentioned before as denominators. The intersection of the original algebra with the circle of this algebra is just the set of Le-Chicroso elements. Okay, so this is the importance of this notion. Now, so in contrast with what I said here, the regularity condition at which usual rings of quotients aim, which is making invertible the regular elements, because since they aimed at for the orders, there is another condition which is making the elements what is called locally invertible. So this is invertible in a suitable local algebra. I will be more explicit about that. But this approach suits the purpose of defining a Goldie-like theory for Jordan pairs. So what happens for Jordan pairs? Well, for Jordan pairs, of course, you can try to make invertible some elements, but if you succeed at that, it's because your Jordan pair is in fact a Jordan algebra. I mean, you cannot have invertible elements in a proper Jordan pair, which is not an algebra. So in fact, how to define a Goldie-like theory for how to localize Jordan pairs? Well, you cannot do that making elements invertible. And so the approach is slightly different and goes through what is called local Goldie theory, because Jordan pairs are related to Jordan algebras through their local algebras. I mean, the definition of local algebra that I have just mentioned, which is the quotient of the homotope by this quotient here, the quotient of the homotope by the kernel, works exactly well, perfectly well for Jordan pairs, and allows to relate Jordan pairs and Jordan algebras, pairs and algebras. Okay. So this is what is done. The idea of defining a localization using this was originally posed by given by Antonio Fernández López and López-García, and goes through this notion. Instead of making invertibles an element, what you do is some regular elements. What you do is making locally invertible some semi-regular elements. So all this is kind of putting things in the two local algebras. Okay, and this can be done with on the ascending chain conditions, which are local ascending chain conditions, to define what we call for an this here the theorem is I mean the properties are explained for displayed for an algebra, but as we will see in a moment, this extend to pairs, and the properties are the following: for any semi-regular element, there's something missing here. Well, in fact, what you do is that you can make locally invertible any element in a local algebra. So invertible any, I mean, you have your algebra, you have an over algebra, and you can make invertible any element of the over algebra. Any element of the original algebra is a classical order in a local algebra of the over algebra. So this is your being an order transferred to local algebras instead of involving the whole pair, would you go to local algebras? So to algebras again. Now you have this. You have the following theorem. In particular, this construction gives you algebras of quotients in the sense that I defined before. So an algebra of quotient is an algebra for which the set of denominators are the set of dense inner ideals. I mean, this general notion of algebra of quotients that I mentioned before for Jordan algebras. Okay, so this holds for algebras. So what happens to pairs? Well, this is something that one has to look at. Well, in fact, we have first we have these two conditions for Jordan algebras, and I mean, you have an algebra of you have this algebra of quotients, local quotients. If you have this descending chain condition on principal linear ideals, sorry, if you have an overall algebra with descending chain condition of principal linear ideals. So here, this means that here our notion of regularity is no more the being Artinian or having finite capacity, but having being equal to its circle. Okay, so having descending chain condition for all principal inner ideals, which means being equal to its circle, which is a condition of a regularity condition, but it's a regularity conditions that allows much bigger algebras than just the Artinian condition or finite capacity. Okay, so this leads to the notion of, again, let's check what's ideal for Jordan pairs, and as I said, this can be extended to Jordan pairs, and we can define equally as we did for algebras. The definition is due to Fernández López, García Ruz, and Ja, saying that okay, any as a pair is a local order of a Jordan pair. Pair V is a local order for a Jordan pair W. If and only if for any element of the big pair there exists an element in the small pair such that X is von Neumann regular, Q belongs to Q of X of W, the corresponding part of the big algebra, and the local algebra is an order in the at X is an order in of V is an order in local algebra of a W at X. Okay, so then being the notion of being an order for Jordan pairs in this definition transfer to from the whole thing to local algebras. Okay, and this works pretty well. So at least for Jordan pairs. Okay, and so we have well, the question here is that we do not have a general notion of the Jordan quotient or Jordan algebra or Jordan pair of quotients for Jordan pair. We do not have a notion of dense inner ideal for Jordan pairs, which is an open problem that should be quite interesting to deal with. But for the moment, what we have is that something that any algebra of quotients, classical algebra of quotients, satisfies is that which is that they are innerly tight extensions, which means these conditions here. So any principal ideal of the extended algebra meets the original algebra, and the set of denominators is an essential inner ideal for any element of the big algebra. Now, so in this case, you have that a Jordan algebra is an order sorry, so if you have an innerly tight extension, then you have the property similar to what I mentioned before. The intersection of the circle, sorry, if your innerly tight extension equals its circle, then so it has this chain condition on principal inner ideals, then the original pair is less equals, which is part of the theorem that we are aimed at. I mean, the generalization of what we prove for algebras to pairs in order to define a pair of quotients. Okay, so this is part of the proof, scheme of the proof. So let me see times it. Okay, and what we have is the conditions of being an order, a local order for Jordan pairs, which are, I mean, basically go to the looking at local algebras as it should, and this is what should be. This is the plan to generalizing the notion of a classical order for pairs instead of algebra. So instead of making invertible elements, some elements that you cannot for a Jordan pair unless this is a Jordan algebra, what you do is, okay, you do that locally, because locally you have algebras, okay? And locally you say, okay, your element may not be regular because what does it mean? You can speak about locally regular elements, and what you get is local invertible elements in the quotient. So the local algebra is in the bigger pair. The local algebras are algebras of quotients of the local algebras in the original pair. Okay, so that goes. Instead of working for the whole thing, the whole pair, you work because this is not an algebra, which you work for the local algebras, which of course are algebras, and there you can use the usual definitions. Okay, so this is the object of study, and this is a rather this is a promising way to generalizing the Goldie theory for pairs. For pairs for Jordan pairs, and that's all. So thank you very much.
Thank you, Fernando.
Yeah.
Other questions? There is one question.
Mm-hmm.
It was not a question in the chat. It was a message.
I didn't see that.
John, do you want to ask a question?
Well, if you don't want to ask questions, I can say more things.
Yeah, he has written something in the chat. Maybe it was by mistake.
I don't know. I didn't see that.
Oh, wait.
Mm-hmm.
Well, if not, thank you, Fernando, once again for the talk, for
Thanks.
accepting the invitation. I also thank all the participants for your attention and wish you all. So John, yeah, he just said thank you.
Oh. Yeah, welcome.
Yeah, so thank you very much, and
So
wish
thank
you
you.
all a nice week. See you all
The same to
next
you.
Monday.
Okay. So bye.